In 1874, Georg Cantor proved something so unsettling that one of the greatest mathematicians of the age, Henri Poincaré, called it a disease from which mathematics would one day recover. Cantor proved that some infinities are larger than others. Not in a vague sense. In a precise, provable sense. The infinity of counting numbers is strictly smaller than the infinity of real numbers. Between any two whole numbers, the real numbers are a qualitatively larger infinity. Infinity is not one thing. It is a hierarchy of things. To compare two infinite sets, you need a new tool. You cannot count them, they are infinite. Cantor's idea, two sets have the same size, or cardinality, if you compare every element of one with exactly one element of the other, a perfect one-to-one correspondence, with nothing left over. The even numbers and the counting numbers have the same cardinality, pair 2 with 1, 4 with 2, 6 with 3, and so on forever. No even number is left unpaired, no counting number is missed. Intuitively, the even numbers are half of the whole numbers. Cantor says they are the same size. Infinite arithmetic breaks intuition. Now, are the real numbers the same size as the counting numbers? Suppose they were. Then you could list every real number between 0 and 1, first one, second one, third one, infinitely. Cantor showed you cannot. Take your list. Look at the first digit of the first number, the second digit of the second number, and so on down the diagonal. Build a new number by changing each digit. If it was 5, make it 6, if it was anything else, make it 5. This new number differs from every number on your list in at least one digit, guaranteed. So it is not on the list. But it is a real number between 0 and 1. Your list was incomplete. Every possible list is incomplete. The real numbers are uncountable. This is not the end. Cantor proved you can always build a larger infinity. Given any set, the set of all its subsets is strictly larger. So you have the counting numbers, called Aleph null. Then the uncountable real numbers, called the continuum. Then the set of all subsets of the real numbers, larger still. Then the set of all subsets of that, larger still. An infinite tower of increasingly large infinities, each one dwarfing the previous. No largest infinity. Even the concept of all infinities is too big to be a set, it forms what mathematicians call a proper class. Cantor spent years trying to prove or disprove a question he could not answer. Is there an infinity between the counting numbers and the real numbers? A size strictly in between? He could neither prove there was nor prove there wasn't. In 1900, Hilbert listed it as the first of his famous 23 unsolved problems. In 1963, Paul Cohen proved something extraordinary: the question cannot be answered from the standard axioms of set theory. Both assumptions are consistent with mathematics as we know it. The continuum hypothesis is, in a precise technical sense, undecidable. It is one of several true mathematical questions that have no proof within the system we use. Cantor's contemporaries called his work dangerous. Kronecker, one of his teachers, called him a corrupter of youth. Cantor suffered a series of breakdowns and died in a sanatorium. Today his theory of transfinite numbers is the foundation of modern mathematics. Every working mathematician uses set theory daily. The lesson is not comfortable: infinity is not a single idea at the edge of the large. It is a landscape with its own geography, its own towers and chasms, and the map is still being drawn.